Welcome to the second talk by Walter van Suijlekom in ISI Kolkata. So the title of his talk today is Inner Fluctuations in Geometry. Walter.
Okay, thanks. All right, let's continue on what we were doing yesterday. Of geometry. And I will start with a recap of the objects we were looking at yesterday. So we looked at spectral triples. Which were kind of the replacement for Riemannian spin C manifolds. And this was a star algebra of bounded operators. This is a Hilbert space. This guy. And this is an unbounded self-adjoint operator such that the commutators extend to bounded operators for all A and A, and the resolvent of D is a compact operator. And if A is, so I said something about this yesterday, if A is unital, then this is actually the list. If it's not unital, then you put something in front here, an element in the algebra, so to localize it essentially. The examples we looked at were, of course, the first one. By the way, today I will be doing things very example-based. I will give many examples of noncommutative spaces and of fluctuations. So the first one is a manifold M with a Riemannian metric and a spin C structure. And then one of the things we established yesterday was that you can reconstruct the metric from this data. Okay. So there was a formula D xy supremum over F. Which actually captures the Riemannian metric. By the way, if there are questions about this, then again, that's a good opportunity. So if there's something unclear from yesterday, then I will also give some other examples now, which are actually quite useful, and they're even easier than this one. So it's the algebra is C2. Think about them as diagonal matrices, like lambda 1, lambda 2. So that's the algebra structure. It acts on C2, where that's like a vector. And then D is some matrix. So it's here it's said unbounded, but in this case, of course, nothing can be unbounded. So it's a bounded. It's just a symmetric operator or Hermitian matrix D, which I take to be the following. In fact, this is the most general thing you can do. I mean, the zero on the diagonal, you can put something there, but they will commute anyways with the algebra. So they're not so relevant for these kind of considerations. So that's the thing. So this sits in there. And C2, so if you think about what it describes 2 points. Okay, because C2 is like continuous functions or functions on 2 points. So the characters of C2, 2 points, 2-point space. So And so topologically, that's what I do. Discrete, I can distinguish 2 points. But now I have a candidate for a distance. Even though I draw these points on the board, I didn't say anything about the distance between them, because I can actually compute the distance. Because the distance between 1 and 2, I mean that's the most reasonable thing to do, is the supremum over A, so these are the A's. And then I have something like, well, lambda 1 is the value of the function at 1, lambda 2 is the value at 2. So I look at the difference, lambda 1 minus lambda 2. So that's my characters applied like with the functions, with the constraint that the commutator of D with A in operator norm or matrix norm is smaller or equal to 1. So let's compute this. I guess that's actually not too difficult. So D commutator A, and this is actually quite fun because you can do concrete computations with this, where this formula applies. So dA, so this is like, if you think a little bit, so it's like lambda 2 minus lambda 1, C, and then lambda 1 minus lambda 2. And remember that this is the supremum norm of an operator. So it's like it's just the largest eigenvalue of such a matrix. And the norm for this matrix, I mean, you can try to diagonalize maybe or do something more clever. Maybe take the C star property into account, but you can compute that. The norm is C lambda 1 minus lambda 2. Okay. So that's something you can check. So this has to be smaller or equal to 1. And then I want to take the maximum over lambda 1 minus lambda 2 with that constraint. So this should be like that. But this means that, well, you can maybe flip that to the other side, that this distance is actually 1 over C. This one. So the parameter that I get in D, this thing here, it indicates the distance in, of course, the reverse order. So this distance here is captured precisely by this operator D. And that's kind of the advantage of working with this, because so nothing is non-commutative yet, but still this framework allows to describe spaces which are not a priori geometrical in the usual sense, but they're like spectrally defined, and then they do give rise to something like a metric. So I have the third example. This can be done quite quickly, but it's good to have it for later. M and C. So n by n matrices. That's our first non-commutative example, by the way. So matrices are non-commutative. They can act on Cn. And D can be, again, some Hermitian matrix. So this is automatically, it does the thing we were after. So, but it's I will kind of leave it with that. Let's see. I would like to have maybe one or two more examples. So the first is actually a serious non-commutative example, which is the non-commutative torus. It's also one of the oldest. So what you do is you take unitaries U and V. So this was actually at the beginning of the whole field. I mean, in the 1980s, this was the example that was actually driving the definitions. So lambda is e to the I theta. Theta is some real number. And then you look at the algebra where you consider these unitaries as if they were like trigonometric exponentials on a torus. So you look at series this type. And I take these AMN sequences, these coefficients of rapid decay. So like Schwarz, so they're under control, which means I look at smooth functions essentially, because they have that property that the Fourier coefficients will be of rapid decay. So then there is okay, that's the algebra. It's a star algebra as well. These are complex valued, so this all works. A Hilbert space, I get as follows. So there's a faithful trace tau, which takes such an element here, and maps it to its 0, 0 Fourier coefficient. It's as if you're integrating a function over the two torus, then also the only thing you pick up is the 0, 0 component of the Fourier expansion, right? And this is how it's defined now, because I don't have that Fourier theory here. But what you can do with that, you can introduce an inner product. Two elements here. I can take the inner product, A star B, like this. And faithfulness means that A comma A, which is tau of A star A, is 0 if and only if A is equal to 0. So this is an inner product. It's actually, it's a pre-inner product. So this gives rise to H theta, which is just L2 with this tau. So it's the completion that you get from A theta with this inner product. And A theta acts on there, you can check that. But it's like GNS. I mean, I get it's like the GNS construction that you probably know. Now for D, I need two ingredients. I need derivatives. So I need derivations, which are the following. So this is U. I have two derivatives, one in the first direction and the second one in the other. Oops. And if you look, I mean, this is like e to the I and then t or something like this, t1. So you get e to the I t1 back if you derive that. So this is what you should do. So it's all in exponents. This is v. And they combine to give you just as the Dirac operator I wrote yesterday on the two torus, to give you something like this. So let me stand aside. So that 2 by 2 matrix is the one I wrote before with the partial derivatives, but now I write it with the derivations. And it actually acts on H theta, tensored with, I should do that probably, like before with C2 to get these spinors. And then this, so first of all, if you compute commutators, then you find that actually the commutator of D with an element in A theta is just bringing down these M and N. But since these sequences are of rapid decay, this is still okay. So it's bounded. And also the resolvent is the same, because actually the spectrum of that D is the same as the spectrum of the classical Dirac. So this is, so A theta, H theta, and D. Let me call it D theta as well. So that's the non-commutative torus. Okay. And then I found another one, a new spectral triple, which I will call a PCM spectral triple. But that's just because I got inspiration from, so I'll try again, Prasanta Chandra Mahalanobis, you know. So I gave this as I suggested this as an exercise. Can you find a spectral triple which reproduces the PCM distance? So anyone came up with a... So I have at least a proposal. So first of all, the idea is that you have a probability distribution on Rd. So there are D random variables. And it has a covariance matrix, which is positive definite, just by definition. Sigma. Then what this distance is, that Mahalanobis introduced, is that it's x, y, and it depends on rho, on the probability distribution I started with, where he looked at Gaussians, by the way, but that's fine. It's actually So it's defined like this. So this is the inner product. The Euclidean. I should probably just write it like this, because I put the dot. It's 1/2, which is actually it's the Euclidean distance after the so-called whitening transformation. So you take W, it's sigma to the minus 1/2. So this is the distance he introduced to analyze, well, to understand distances in the presence of a probability distribution. And this W here, as you see, I mean, if you transform with this one, you will find that you are actually moving your distribution to a standard one, which is Gaussian in all directions. So they're then independent, and that's why it's called whitening. But I'm not an expert on this. I just have now the proposal for the spectral triple, which is much more in my comfort, which is the following. So it's non-unital, to be a little bit careful, but so it's CC infinity on RD. Then I have L2 RD, and then times C to the 2 D over 2 as before, this integer part. And then my D is I claim to be the following. So I take mu is 1 to D, and then I have gamma mu. And gamma mu are flat gamma matrices. Then I have my W inverse, mu, nu, del nu. So gamma mu, gamma nu, they're flat. So if you take a Dirac operator, the usual Dirac operator on RD will be the one where this is not present. It's just gamma mu del, or it's like the delta del mu. Let's put an I in front to make it self-adjoint. And so this here is the kind of the only thing that changes. So what I do is actually in front of my partial derivative, I have a combination of gamma matrices of different types that are indicated by this whitening process, the inverse of that.
Is this something like your Feuerbein's?
Yeah, it's like this, because you change indeed. I mean, already here you're changing your space by putting it into another configuration, another kind of combination of the different directions, and that is then an orthonormal in a sense. What you're saying. So you're changing the actually what you find is that the metric that this describes, the remaining metric, is actually sigma. So that's so this covariant matrix is the metric that you're trying to describe, and you relate it to delta mu nu. So it's precisely in that sense a Vierbein. So to make it, and so in that sense, you can show that if you compute this distance, you get this distance of PCM back. So that's a nice. Would attribute it to this institute, I think. And maybe there's something more we can say about that. So maybe this visit opens a whole new field of applications of spectral triples. I mean, for instance, tomorrow I will talk about entropy of a space. So maybe it's possible to compute it, and then who knows what this says. But
I want to ask you, there are some non-commutative spaces where probably spectral triple description is not possible, like Kappa-Minkowski spaces and things like that.
yeah, so the signature, it's like Minkowski. It's that's more difficult. Not possible is always
No,
tricky.
even with Euclidean signature, Kappa-Minkowski with Euclidean signature.
Well, there's attempts that failed, I guess, right? So it's not clear if it's not possible. So this is not. I mean, like with the quantum groups, there was also, of course, there were proposals, and in the end, that worked out. So for several cases. So I don't know if there's an obstruction in general, but it's true that it may not be easy. So the theme of today, because this was still the recap, symmetries. So it's about symmetries of this object. Okay. So what you may wonder is, okay, let's say you can look at star automorphisms, for instance, which seems reasonable. So that's an automorphism group. So these are just all linear maps that respect the product in the star structure. In there, there's a subgroup, normal subgroup, which is generated by inner automorphisms. And they're of the following type. They map A into U star, where U is a unitary in the algebra A. And these are sort of so this inner that is named here, that's the origin of the name inner fluctuations, because it's about well, it's related at least, because the algebra, the non-commutativity of the algebra will generate these kind of this kind of symmetry. Let's illustrate this with examples. That's probably the best. They tell me a little bit what kind of symmetries we're looking at. So, in the case of C infinity M for some manifold, the automorphisms there's no inner automorphism in this case, because this here, U star, I mean this product is commutative, so you can just push it to the other side and you lose the U, so it's just A. So no inner, and it's just a general phenomena. No inner automorphisms. But there are outer automorphisms, so it's all the rest. And they happen to be given by diffeomorphisms of M. So by pulling back, you can go between the two. So if you have a diffeomorphism from M to M, it induces an automorphism of the algebra algebra functions, and the other way around. It induces a diffeomorphism. So this is this kind of the case that there's no inner, and there's the other extreme. That's Mn of C. Then there are no outer automorphisms. There are only inner automorphisms. So all aught is actually in. And so inner means, so you take a unitary, except that there is a kernel to this map. So by mapping a unitary to alpha u, of course, if you take something in the center, that will also disappear. So in this case, it will be u n over the center of un, which is also called pun. Yeah. So in this case, everything is inner, and so the difference between these two is really extreme. And so this is like also explaining a little bit why. So we talked about this a little bit yesterday. If it would be possible to generate the metric using this prescription of inner fluctuations, but here you see that they're already kind of split in two directions, where this is much more on the geometrical level of M, and this is much more in the sort of a gauge direction, which is not present in that case of M, so where the metric lives. Okay, so how does that work for spectral triples then? So if we focus on these inner fluctuations, they have the special property that they can lift to an operator. I mean, they are actually operators on Hilbert space. As a unitary, of course, as a unitary operator. And so they induce a transformation on D, because I can have an operator that acts on H. So this unitary operator can be used to intertwine, to kind of conjugate D by U. So U D U star. So the spectrum is the same, of course, because it's unitarily invariant, equivalent. But there's a nice way to write this, because I can write this as D plus U du star. So this is what you get when you kind of generate this, take this unitary operator to generate another Dirac operator. It is the same in terms of the spectrum, but not so as an operator. So it's D plus this term, and this you can just check by writing U du star minus U star D. That will actually cancel. So this means I have a linear perturbation of D. And this one here is given by something which is a commutator of D with U star, which we assumed in the first place to be bounded. And so is U. So this is a bounded operator perturbing D. So this is kind of the first instance of where you see something appearing. And I would like to view them as one forms. So this is like what we call pure gauge one form, and I will make this one form aspect more precise in a moment. So it's like what I will do is I view D commutator as sort of a differential, and in that sense I can view this as U du star, and that's the term that you add to an operator such as D to couple it to a gauge field. And in this case it's pure gauge, so there's nothing actually going on because everything is gauge equivalent, where this is like a gauge transformation is unitary, so nothing is really happening, also in physics. But later on we will see that that will, when we generalize this, then it will actually change the operator D, also its spectrum.
Just I wanted to, I'm a bit confused about one point. When you say that automorphism A is inner automorphism, I thought inner automorphism is a normal subgroup of automorphism, you know?
Yeah.
Then why are you identifying automorphism A with inner automorphism? Normal subgroup? Or?
Yeah, but now it's everything. In MNC there's nothing left. So this is of course a normal subgroup in automorphisms, but it's actually the same. So it's not proper, but it's still a normal subgroup. But it's everything. So yeah, this is like this. The quotient is what we call the outer automorphisms. But
yeah.
So the quotient.
So outer automorphism will be related to diffeomorphism, right?
Yeah, that will be this one. But that's in this case just because there's nothing. So this is outer. But if you take the combination, that's a good point, this one, then the automorphisms will actually be a semi-direct product of these diffeomorphisms. And so let's see, it's C infinity M with values in this PUN. And a semi-direct product with the diffeomorphisms of M. So these diffeomorphisms, they will kind of act on that. And this is coming from that part by combining it. And that comes from the bottom part. But now you see they're actually combined. And that's because this I know what these things are. Yeah. So this would be the inner part. This is the outer part. Right. So well, this is all nice, but it's so it gives me a notion of symmetry, but it's also a bit confining because I have a symmetry which is doing nothing to the spectrum. Okay, so nothing's really changing. So I want to kind of extend it a little bit, and also to something which is more appropriate for non-commutative spaces, and that's called Morita equivalence. Mhm.
Well, what is the reason to think of them as one form? Do they define like a derivation on your algebra or something?
Yeah, they will in a moment. Yeah. So the D. So I will introduce one forms, which I denote like this, and they will map A into the commutator of D with A. And there will be one forms, and I can multiply them with functions, but they will be like in my model for one forms, differential one forms. Yeah. So yeah, Morita equivalence for algebras. So A. Let's do B Morita equivalent to A, but it's the same thing. So that's an equivalence relation that I will introduce, and I will introduce it in a very kind of concrete context of unital star algebras. And I will use a little bit of module theory. So it's about modules on algebras. So I will write something like this for a right module. So it's just a vector space carrying a right action of the algebra A. I will use this kind of notation for endomorphisms. I also have homomorphisms from E to F, both of that type. So these are just the right A-linear maps from E to itself, and these are right A-linear maps from E to F. So it would just kind of extend what we usually do with vector spaces to rings or to algebras. And we take E, we call it finitely generated projective. That's if it's a direct summand of a free module, but concretely it means if there exists the projection P in M and A such that E is actually P A to the N. So these are n copies of A. So that's a free module over over A, and the projection is the direct summand. Okay, so that's the way I would like to view them very concretely, but it's what you're probably used to in some other context. So it's a direct summand. And of course there may be more P's available. But this is not so difficult to get from one to the other. So there is a kind of a supplemented module that gives you the free module. Is this clear, by the way? So modules. So the definition of Morita equivalence is that so I take B and A. I think I call them. It's about the order here. So two unital star algebras. A and B are Morita equivalent if there is exists a finitely generated projective module E, which is finitely generated projective for the right A action. So let me write it as such. As a right A module. And it's also such that that B is actually the endomorphisms that I wrote here of E. It's isomorphic to the endomorphisms of E, which are right A linear. And so usually you don't have this finitely generated projective. It's more general. You take any module E and another module F, and you go back and forth. But it turns out for unital star algebras you can do it like this. So unital tells me that you can make it finitely generated projective, and star allows you to introduce also this projection. So we have a way to go from, maybe let's make a comment about Morita, because Morita was looking at representations rather than such a kind of a very hands-on formulation. So the remark is that such an E induces an equivalence of categories. Okay, no. So it's like, so it's representations of, which means modules over A to modules over B. It means you take something like V or so. Now, how does that become a representation of B? It's using this bimodule, which is a BA bimodule. So I just tensor it with this over A. Okay, and this tensor product, this means that I can kind of freely move elements of A over the tensor product. So it's a balanced tensor product in which you identify, so there's a quotient construction going on, something like this. Is identified with eta tensor AV. Yeah, so you can move this, that's what this notation suggests, you can move A over that thing. And you can also go back, and then you have to do something, well, with the other module that you get out of E. But now you use the B action, so it's a representation of B, but it becomes a representation of A by taking the so-called conjugate or conjugate module. Which is sort of, so it uses the star to kind of flip the A and the B action to the other side. So that's, so this becomes an AB module. But it's actually defined directly in terms of E, which is an AB bimodule. So the star, of course, it flips. If you act with the star on the left, it's actually a right action. So if you define that carefully, then you can flip these two using the star in the star algebra structure. All right, so this is what we have. Oh yeah, some examples. It's always good. So the basic example would be, you take A to be C, and then you take the the module E. So this should be a finitely generated projective module over the complex numbers. This is just a vector space. So this is Cn. Then the endomorphisms of Cn to itself, which are C linear, these are just matrices. So the Morita equivalent algebra, B, is, in this case, just M and C. Yeah, so you find that that C is Morita equivalent to M and C, which sort of confirms the thing you know about representations of M and C. There's only one for M and C, only one irreducible, up to unitary equivalence, just because there's only one for C, just by acting on itself by C. By the way, this is different for groups. So for algebras, there's not many representations. If you think about classifying the irreducible representations for algebras, there's simply a single one for M and C, which is completely different with respect to groups, of course, because then you have a whole list, typically, of representations. But the fact that it's an algebra really restricts this. Then if A and B are commutative, then the nice thing is that we actually capture the previous notion of equivalence. So we have a choice, because A and B commutative, then A Morita equivalent to B if and only if A and B are isomorphic. And that's really strong, because it means that when I was talking about automorphisms before, then A and B are isomorphic. It's just the same as putting the Morita equivalence in place. So that's just as good a definition to for symmetries or equivalences if you want to generalize it to the non-commutative world, because in the classical world they're just the same concept, but not so in the non-commutative context. That's completely different. You see here C and M and C are Morita equivalent, even though if you think about them as an algebra, they're completely different. This is non-commutative, this is not. So that's kind of striking. I mean, representation theory, that's similar, so that's why this is the right notion to consider. And this is the equivalence I would like to kind of further develop also in the context of geometry.
I just have a small confusion. Is the projective module that you have taken, is it a left A module?
No, right A.
Then the notion of representation means left A module for you.
Representations, yes, yeah.
Ah, okay.
Yeah, so representations are left A modules. And there I take right modules to start with. Yeah, so that's how it will work. Yeah, thanks. Yeah, if I have to think that a representation of an operator is right, it will be very complicated, because you cannot write it as an operator. But of course, for modules we do this all the time. So it's. But here it fits nicely. There's a proposition that I will only state, that if EA is finitely generative projective, then there exists a Hermitian structure, or an A-valued inner product. On E. So it's something like this. So it takes two elements and it gives an element in A. So it's like an inner product, but not in the complex numbers, but it's in A. But since A is a star algebra and we think about them as bounded operators, there is a notion of positivity. So we can state all the things that we know for an inner product, like the right linearity and so on, in terms of the algebra A here as well. So nothing really changes, but let me actually refrain from writing it down, also in view of time. So let's take this, and now see. I mean, this is actually a crucial ingredient to try to address the following. So we have say we have some geometry on A. Say AHD is given. So that's a spectral triple, and B is Morita equivalent via some E. Can we transfer the geometry to B? That's the question. So can we induce a spectral triple on B now from the thing we had here? So let's try. Yeah.
Just one question: is the FGP important? Finitely generated projectiveness, or is it like for any Hilbert space you can consider each tensor A as a Hilbert module, and there is something like that?
Then you need a control on E.
Okay.
It's not going to work if you don't have that. So here it's very easy because it's finitely generated projective. If it's a Hilbert module, it's still fine. I mean, that's okay. A Hilbert module tensor, a Hilbert space will be a Hilbert space. That's okay. So the only thing you need is a Hilbert module structure, but which is something like this, and completeness. Here I finally generate projective, so I don't need completeness, so it's much easier. But you're right, is that if you take a Hilbert module, it will also work. But then you're doing a Kasparov product, so which I tried to not to do this week, maybe next week. But well, we do it outside of this lecture this morning. So let's try to build something B H prime D prime. So as you say, H prime, it's like the thing I just said. I will move from the Hilbert space H to something which carries an action of B now, and I do this in the same way. This is a Hilbert space because I have an inner product here, which I can combine with the inner product there. So it's like a tensor product, Hilbert tensor product, inner product, something like this. It's a combination of these things, which I will, well, can try to write down. So let's do V1. So this inner product on H prime, this will be V1. And then I take this eta 1 and eta 2. That will be an element in A, it's A valued, which I can have act on V2. So this is the formula. There's usually only one thing you can write down. You just have to kind of find the right formula by playing maybe with it, but there's only one thing you can do because it will act on H. Okay, so this is very good. And the action of B, it's of course on this E. And it's even better because this can be identified. So it's PAN, tensor A with H. And here you can play with, because this is n copies of A, but this is balanced over A with H. So I can actually turn this into n copies of H. So this is PHN. So as a Hilbert space, now it's very easy. I just take n copies of H, and I take the closed subspace, which is the range of the projection P. And that's, of course, a Hilbert space. So even that could work. And that's, of course, because the inner product is of that type, coming from this P. So this is actually the nice thing to look at. So let's try D prime then. And I have a D available, and that acts on H. So the thing to try is something like this. But then there's this issue with the A. It could move over to the left and the right, but D does not commute with A. So if I look at these two elements here, for instance, so I have something like, well, this one. So D acts on V. It acts on the second tensor. But here it acts on AV. But it's not the same thing, because D will not commute with A. Actually, it will give you a commutator of D with A. That's the kind of defect of this formula. So this I repair by a connection, introducing a connection. And this acts as follows. So first of all, the formula is that it's eta times V. That's nambla of eta, V, plus eta tensor dV. So this is the formula I wanted to write, but I have to repair it with a connection because I want to lift it to this kind of this tensor product. And the nambla is a connection on E. So nambla of eta, it satisfies some Leibniz rule. And here is where I have to define this, these one forms. Take some space. So the one forms here they're of this type. So there are elements in the algebra that generate sums of this type, finite sums. and that will be sufficient to actually to repair such a connection. So first of all, these omega 1 dA are now bounded operators because they're of this type, and so they can act. So here namla eta, that will be an element in E tensor omega 1 dA that will act on on V, and here eta is just tensored with the vector in the Hilbert space. And now it's well defined because of the connection. So this is very good. There's actually a result that tells me that after this kind of preparation, that B, H, and D prime is a spectral triple. So this requires a proof which I will only sketch in a special case, which I will come to in a moment, because it's more or less the same, but slightly more involved. It's also in, actually it's not so well presented in the literature that this holds, but so then I took the, paid the effort to write it in my book. It's scattered around in the literature, but okay, so finally, let's, oh yeah, there's one thing I need to say. Provided, that condition I didn't say, this namla is a Hermitian connection. Which means that this, there's it's like a Hermitian or metric. There's a compatibility with the metric or the inner product of this type. And that really makes sure.
Very similar to Kasparov product, right?
This is a Kasparov product indeed. Yeah, it's a Kasparov product with a finitely generated projective module, which represents a class with a zero operator. So it's so this is the unbounded version of the, or representative of the KK product, where I take E, and then I need an operator, which is 0 in this case, with, that's a tensor, over A, with H and D. Yeah, right. And this S can be taken to be 0, precisely because it's finitely generated projective. So the resolvent is compact, even though it's the 0 operator. And otherwise, so if you think about Hilbert modules, so X, comma S, so there's a notion of this as well. So as you asked this before, so this can be a Hilbert module, then you can make a Hilbert space out of that. And then S, if it's a suitable operator on X, so regular self-adjoint with compact resolvent, then you, in some cases, you can also write the formula to make this in terms of as a spectral triple. Here the people who are most involved in this are Bram Mesland, Jens Kaat, and Matthias Lesch. So there's a few of these papers that treat this very carefully. The papers I wrote on this are actually example driven. So there's some kind of classes of examples where I'd like to kind of factorize some operator as a Kasparov product, and that's motivated then by some Gauge theory consideration. But so let's.
So first one is the KK class of Morita equivalence. So E.
Yeah, so that's right. So then the Morita equivalence is a special case of yeah. As a special case of KK equivalence, is that what you mean? Yeah. There's another special case of that, which is Morita self-equivalence. So it's just going from A to A. So my B is now A, and E is A. So that seems rather boring, because nothing is really happening, because H prime now something like, well, it's A, tensor A with H, so that can just be multiplied, so H prime is simply H, B is A, H prime, but D prime, this has this extra connection term, and that's actually, for at least in this unbounded situation, it's relevant. So it adds a term, and it's omega. This is the connection evaluated at 1. So omega star is omega, which is the connection at 1, which is an element in omega 1 dA. This really happens if you write out what one tensor lambda d becomes after multiplying out this algebra element A, because then only thing that is left is the identity then.
Sorry, lambda is the connection on E, right?
Yeah, but E is A.
Oh, sorry.
Yeah, so I can actually multiply everything out. The only thing is left is 1. So I only need to know lambda on 1. And everything else is generated by the Leibniz rule. And so this is what I'm left with, d plus omega. And omega is then, of course, as I wrote, this bounded operator of some type, some AJ, BJ. And let me actually show then, check. So first of all, self-adjointness. So if you have a self-adjoint operator D and you add a bounded operator to it, which is also symmetric, then it's not too difficult to check self-adjointness. The other thing is the resolvent. So let me check it here, because I didn't do it for the theorem, but here I can do it. And it's, in general, it's the same formula, because there is a very nice expression that you may know from your functional analysis course, or from fractionals. It's the same expression. So you could try to kind of, I mean, if you look at this a little bit, and then you see it's true, because this 1 is like I plus d plus omega times I plus d plus omega inverse, and then you subtract the omega to give you precisely this I plus d, which you cancel. So this is a formula you can check if you wish, but it's a nice formula, because I want to know that this is compact. So that's my question. But this is compact, because I started with something which is a spectral triple. So I know this is a compact operator. And this is 1, okay, fine. Omega, bounded. This is something which is also bounded, because it's a resolvent. So this thing is just the bounded operator. So I have a compact times bounded, which is compact. And that's it. So it's a very kind of straightforward formula. And this also works in this case, because this d prime can actually be written as PDP plus omega with that same p. So then you kind of have to look at PDP and omega, apply the same reasoning, so then it reduces to PDP. So it needs one more step, but that's all possible. Okay, let me finish by a few examples of this. Because we now have sort of a machinery to generate new operators d. So it's d plus omega. So this is my new Dirac operator that is kind of generated by the algebra. And how does it generate? It's this combination of elements in the algebra. I just look at all elements in the algebra, AJ and BJ, see what kind of omega do I get. So let's look at the first example, which is this C2 like this. So the first thing you have to compute is what is omega 1 dA. So, and for that I have to compute all these kind of commutators. Now I did already one, which was this commutator which had this lambda 1 minus lambda 2. So it's something like C, let me call it mu, and here is C bar, mu 2 minus mu 1, something of that type. And here is lambda 1, lambda 2 in front. So this is all the things I should consider, where lambda 1, lambda 2, mu, and so on, they're complex numbers. this doesn't really add too much to it. What I find is that this new thing looks like this. So it's that type where phi is a complex number, phi prime as well. And C is the one I started with. So actually you see I can rescale my constant I started with. I get all possibilities for C. And if I impose the self-adjointness of this element, this omega, I find that d plus omega will actually be something of the form 0 C 1 plus phi C bar 1 plus phi bar. So you see I can sort of tweak now the distance between these 2 points by letting this phi vary. And in physics, it's not for nothing I call this phi, because this is a first hint of a Higgs field, a scalar field that appears in particle physics. That will actually play the role between these 2 points in the particle physics applications. So this is sort of a zero-dimensional version of a Higgs field. Okay, here's another example. Actually, my last, which I do in more detail, and then I'll stop also, which is MNC on Cn, and D is a Hermitian matrix, but it's not proportional to the identity. Otherwise, nothing would really happen, because these commutators will be 0. So then, so let's try to compute omega 1 dA in this case. In the same way, it's just a task we're given. Okay, compute. So something like M. Now let's actually do it more cleverly. So what is this? So let's take D to be some matrix, lambda 1, lambda 2, etc. And let's suppose lambda 1 and lambda 2 are not the same. Okay, so I can kind of shuffle my I diagonalize D to start with. And I put, since I know it's not proportional to the identity, I know that 2 of these will be different. So let's take them in the first, in the corner. So then I can compute D with E12. So this commutator is lambda 1 minus lambda 2, which is non-zero, times E12. So E12, by the way, is the matrix with value 1 in the 1, 2 position and 0 elsewhere. So that's already good. Now I can multiply this on the left with, say, EI1, and then on the right maybe with E2J. Then I get lambda 1 EIJ. So these are, my notation is always the same. So this is ith row, jth column. There's a 1 and the rest is all 0. Okay. So I can generate, using this, actually all matrix basis vectors for my MNC, multiplied by this lambda 1 minus lambda 2, as long as I just keep adding these things, which I can because it's a sum in this omega 1 dA. So this means that if I have that D, such a D, I can generate any matrix. So this here is actually just MNC itself. So I can generate any matrix from such a D by doing these kind of inner fluctuations. But what does that mean? I can, first of all, it means that the D plus omega becomes, so the set of inner fluctuations can be any matrix, any Hermitian matrix. In particular, I can take omega to be minus D. Okay. So it can be the 0 matrix. So omega can be minus D, because that's a special case. Okay, so D plus omega, the fluctuated D prime, is 0. But now you're in a sink in a sense, because now try to, so what we did is we started from D, we fluctuated, we're in D prime. Okay, let's try to fluctuate again from that point. Now I can again do the computation, which is now one line because D prime is 0. So this is just 0. There's nothing, no form, because the operator is 0. So there's no one forms. Which means I cannot get out of this 0. So I kind of, I sort of fluctuated to 0, but from there I cannot escape. There's no way you can fluctuate away from D prime, which means, it implies, it's an example, which implies that this is not an equivalence relation. You cannot go back. So it's an equivalence relation on algebras, but not on spectral triples. So these inner fluctuations, or the induced by Morita equivalence, does not give equivalence relation on spectral triples in general. This has to do with the fact that this is a very kind of, 0 as an operator is of course not typically not allowed. It's only in this finite rank case, so finite size. So that's rather special. And the third example, which I will not spell out, is about A theta, because there's a very rich theory of Morita equivalence for A theta, which actually has to do with the parameter theta being irrational or not, lying in the orbit of some group acting, some conformal group acting on this, or a Möbius group acting on this theta. And then you can actually show that for this class of non-commutative tori, for different parameters theta, you can, it actually does become an equivalence relation. So there's a nice thesis of Jan Jitse Venselaar, this guy that wrote the thesis in Utrecht from about 10 years ago, I think, on a Morita equivalence. And he shows that then it actually does give a way to go back and forth. So it's symmetric. And here it fails to be symmetric because you cannot get out of this D prime. Transitivity is typically fine, you can just keep generating. But it's about ending up in such a place where D prime is 0. This is a problem. All right. I think that's that's it for now. So thanks for today, and continue tomorrow.
So, questions? Yeah.
As you have shown that Higgs field can be obtained from your fluctuations in the so-called in the discrete direction.
Yeah.
So it may impact the distance, cones distance also, no?
Yeah. It's actually so the distance, I only said it in words. The distance now between point 1 and 2 is actually 1 over c 1 plus phi, something like this. So the this is not, so physically speaking, it's the value of the Higgs field, or say, which is related to its mass. It's inversely proportional to the distance, which is quite natural, right? It's mass versus distance seems to be kind of dual to each other, and so you find that back here. So you can realize this as the mass of the Higgs being inversely responsible, say, for the distance between the 2 points in this space. That's the interpretation. So, and they're not embedded in some space; they're just there. And there's this notion of distance, which you measure. You see the distance using the Higgs field, if you want. That's the interpretation. And this is similar in a sense to the way you view distances in kind of the continuum direction, where you use the gauge fields rather than the Higgs field. So they seem to play the same role, but they act in the different kind of the continuous and the discrete direction. Yeah. But it all fits in the same kind of spectral framework, and that's
So
the
in
advantage of
sense,
this.
conceptually unifying gauge fields with the Higgs field.
Exactly, yeah. And in fact, this task that I was working out for this case and for that case, if you do this for a more complicated spectral triple, which has both functions, so it has both of these aspects. So it has C plus something else, like let's say M2C. So I have a manifold now. I have 2 points. I have a C and an M2C. And I also have this non-abelian property. Then if I represent this in a correct way, and if I put an appropriate D, then you can do this computation again, and then you will find, just by the same computation, in the different sectors you would find gauge fields, and you find Higgs fields. So the Higgs would kind of lie in between these two points, and the gauge fields would be more like this is a U1 gauge field, and that's an SU2 gauge field. So that they kind of, that's how they arise from the same computation, but in different places in the model. But the unification is indeed as such. Yeah. Well, that's the elegance, indeed.
Yeah.
Yeah.
Any other question?
So given A and H, do we know the classes of D which produce the same distance?
Let's see. It's an interesting question. That's not so clear, I think. But you have some control, for instance, by saying if some element in D, some kind of some part of the operator commutes with the elements in the algebra, then you can forget it.
Yeah, so D plus anything in the commutant
Yeah.
of that A would work.
Exactly.
Is the class necessarily bigger?
Yeah. No, but these computations are highly complicated because this distance is indeed computed using it's optimization. So you have some constraints, like this norm should be smaller or equal to 1, and I want to maximize something else. So to actually compute it, to understand it, it's quite complicated. And this is, I think, investigated starting with Riefel, where he talks about compact quantum metric spaces. So it's about actually framing this in terms of a leap norm, like the one I had. So slightly more general, and then you can analyze these different aspects. But it's very hard to actually compute or to understand what is the consequence of this. Yeah, that's a good question.
So, any other question? Sure.
Is there a notion of descent for spectral triple?
For distance?
Descent for spectral triple. Like you have, I mean, you talk about Morita equivalence, and suppose I want to calculate the Hochschild homology or something, and can you break it up into smaller pieces with gluing data such that you can write, say, the module category as an inverse limit of the corresponding module categories? But at the same time, you want them to be like spectral triples, like how you have like Zariski descent or something like that in algebraic geometry, similar fashion.
No, I'm not sure if that's. I'm not familiar with that to start with, but I also am not. I haven't seen anything like that, so I don't think that that may work. Yeah, so there are a lot of techniques that are usually kind of available in that context, which sort of do not easily transfer to this. For instance, the problem of defining the right category of spectral triples is already a challenge. So it's not even clear how that exactly works. There are some attempts. So in particular, Bram Mesland is working on that. So to try to understand what are the right morphisms between spectral triples. And it should sort of capture, this Morita equivalence to start with. So that could be a morphism, but it should be more general like that. So it's, but that's not yet at the status that you're referring to. Yeah.
Any other question? Okay, so if not, let's thank Walter again. So we meet tomorrow again at 4:15, 1-5. But so there is some cigarettes over there. So please join us.
Yeah.
We would like